This is December the 27th, 1990. The Cessna Aircraft Company's 11-year endeavor in the helicopter business is the subject of this presentation. This endeavor was initiated early in 1952 with the acquisition of the Siebel Helicopter Company. The personnel of the Siebel Company then became the engineering core of Cessna's new helicopter division. We will now go back and meet these people. Dick Ledwin supervised all of the division's maintenance and manufacturing activities. Chief Test Pilot Jack Zimmerman, Chief Engineer Charlie Siebel, a long-standing member of Cessna's management team, Sherman Graves, was appointed General Manager of the division. Cessna's corporate staff, they are as follows from left to right. Vice President of Finance, Frank Betker. Marketing Vice President, Don Flower. Vice President of Manufacturing, Delbert Roscom. Charlie Siebel. Engineering Vice President, Tom Salter. Dwayne Wallace, President and Chairman of the Board. At the time of the acquisition, there were two Siebel helicopters on test at Fort Bragg, North Carolina. The Model S-4B had been evaluated at Fort Sill, Oklahoma, as a training aircraft with the two people in front, side by side. It didn't appear that there would be any more orders of the YH-24 tested at Fort Bragg. The S-4B shown here received favorable comments from the training people, but Cessna decided to discontinue any activities with the Siebel line and start over with a clean sheet of paper. The S-4B was flown for a month or two. For familiarization purposes, our general manager, Sherman Graves, took his first helicopter ride in this machine. For about 3 months, Sherman Graves and I traveled extensively. We called on helicopter operators, on the military vendors that we might use later, and he was really getting himself up to speed on the helicopter industry. At the same time, we conducted preliminary designs on the Cessna CH-1, Cessna's helicopter number 1, and we'll now go and take a look at some of these preliminary sketches. On the CH-1, the engine was located in a nacelle at the front of the aircraft. The fuselage was wider than the nacelle, allowing the pilot to have downward visibility through a forward window. The engine drove through a freewheeling unit and clutch shafting to the transmission, which then drove the rotor through a shaft and the tail rotor through an extended shaft to the rear. With the engine forward balancing the tail boom, a major portion of the useful load could be placed right on the center of gravity of the aircraft, about 2/3 of the load. The other third would have to go behind, but the CG travel with this arrangement was much less than any other arrangement. Continental Motors Corporation furnished the engine, which had two cooling fans belt-driven from the crankshaft. The supercharger also was belt-driven from the crankshaft. The transmission employed only 3 gears, all spiral bevel. The input pinion from the engine, then the ring gear that drove the main rotor, and a power takeoff gear in the back that drove the tail rotor shaft. The oil pump was located on the front of that shaft. The tail rotor gearbox employed 2 spiral bevel gears with a 1-to-1 ratio. This is the driving pinion here coming forward from the forward shaft, and the pinion that drove the tail rotor. This sketch was drawn by Richard Tennite, a consultant with Cessna, and with only minor changes in the lines, he was able to improve the appearance. 1952, we proceeded with the design of the CH-1. One afternoon, Sherm Graves came to me and said, "What do you think about boundary layer control on rotor blades?" And I said I wouldn't touch it with a 10-foot pole. Well, he says, "You better figure out why you think it's a good research program, because we're going to Washington, D.C. and take a contract on just that." And it seems that the Office of Naval Research and the Army had placed a contract for boundary layer control research with another contractor who had backed out the last minute, and they needed to get it on contract to retain their funding. So we went to Washington and went in the office of James Wallace McDonald, an Army engineer I'd known for some time, and he said, "Well, Charlie, how are you going to run this program?" Well, I cleared my throat, and he said, "That's fine, that's exactly what we want." So we went home with a contract for research on boundary layer control. The only problem was we didn't have anybody to man it, and we were very fortunate, however. I was able to hire an engineer from the FAA, Mr. Sanford Hinton, who set up the program and ran a good program. They really got their money's worth. The design and development continued, which we'll return to in a minute, but I'd like to mention that we really got a setback in December. Sherman Graves, our general manager, was flying to the East Coast in 170, and he ran into weather and made a precautionary landing at Richmond, Indiana. He was on the runway and rolling out when a DC-3 airliner landed on top of him. The propeller shredded the 170. The airliner, however, made a safe landing. Sherm died instantly. He'd been at Cessna for 16 years, about as long as Dwayne Wallace, risen through the ranks at Cessna to hold a number of different key management positions. He knew everybody in the company, everybody liked him, and he had the respect and confidence of Dwayne Wallace. It indeed was a great loss to the helicopter program. However, we continued on the development of the CH-1, and I worked for Wallace for a short time while he looked for another general manager outside the company. And now we'll return to the development. Historically, the dynamic components of a helicopter require the most development. This includes the engine, the transmission, the freewheeling clutch, and the drive system back to the tail rotor. You note here that the pulley at this location drives a belt, which in turn drives the pump, hydraulic pump, and the generator. Back here is located the tach generator. The reason for locating these components to the rear, of course, is to offset the over-heavy, nose-heavy condition created by the forward engine. The first prototype, the flying test bed, was assembled early in the program. Here we are mating the tail boom with the lower fuselage. Note the erector set tooling, which was used extensively at Cessna for prototype assembly, and was very convenient. You'll notice the clecos here that are holding the structure together before riveting. This is the machining of the lower transmission case. The case is mounted upside down in the milling machine, and the operator is boring the bearing support for the pinion input. These are bosses that support the transmission on the fuselage structure in the final assembly. This particular casting is a magnesium casting. The bed was completed early in 1953. The dynamic components were mounted on a temporary fuselage. We didn't have the upper double curvature fuselage, so we supplemented it with a steel tubing frame. This was a very useful tool in getting the dynamic components into flight early in the program. Here we see the tail rotor test stand, and this was used to measure thrust, an electric powered motor here driving with a belt drive. It, however, was used mostly for endurance testing, and it guided the program very well. The complete helicopter drive system was mounted on a concrete and steel base. This included the engine, and it was operated for 500 hours. The cooling was supplied by electric-powered centrifugal blowers so that the system could be overloaded during a test. In the spring of 1953, Jack Leonard joined Cessna as general manager of the helicopter division. Jack had been with the Goodyear Tire and Rubber Company as the manager of their aircraft division that handled their aircraft products like landing gears, wheels, and brakes, and tires. This is the initial flight of the flying test bed. I was standing by in front as a safety man. As it turned out, Jack Zimmerman, who was flying it, of course, didn't need a safety man, but you can physically pitch and roll the aircraft and help a pilot if there should be a problem. Jack didn't need any help, didn't have any problems. The flight went very well. At this point in time, the machine didn't have any control boost, and stick forces were somewhat of a problem. We did a lot of flying with it, though, had it as high as 10,000 feet, ran lots of tests. This is a torsional survey of the drive system. You will note the torsional pickup on the front of the crankshaft, this location. The purpose of this test is to measure the stresses in the shafting and determine the resonance points in the drive system. Then there is endurance running conducted at these resonant conditions for 30 million cycles to substantiate the system structurally. Stresses are measured in the rotor shaft using the slip rings on the mast. The master reference plaster defined all the exterior contours for the fuselage. You notice it's pivoted to facilitate taking splashes. Here's a splash of or tool of the nose cowl. Richard Tenite's putting the final touches on it. And you can see in the background there the complete cowl plaster. These are all reference tools. A 1/4 scale wind tunnel model was manufactured and tested in the University of Wichita 10-foot wind tunnel. Here we see the model moving through the pitch range. Note the tufts, small pieces of yarn on the fuselage that indicate the direction of airflow. It proved to have very low drag and good characteristics. In the summer of 1953, Sid Shannon, shown here on the left, joined the helicopter division as sales manager and reported to Jack Leonard on the right. This is a landing gear drop test. This is Melvin Vague, project engineer. This is the landing gear, and this is the tension member that stretches plastically. It's a very efficient gear, doesn't rebound. Everybody pitches in and helps on these tests. There's Jack Zimmerman here. This will be another drop condition. efficient gear from shock absorber standpoint. See the lead weight on it there. This is a fuselage static test. The second fuselage was put on test. You notice a hydraulic cylinder applying the horizontal loads. The vertical loads were applied with shot bags that were hung from the tail boom, put inside the fuselage. And the total load was raised to an accelerated flight condition of 5¼ Gs, ultimate loading, and then to a negative loading of 0.75 Gs. This is a lot of weight to go in the fuselage. The mast here goes down to the floor and supports the fuselage. The second prototype was rolled out in the spring of 1954 at the Prospect plant where we were located at that time. We had started on the east side of town in the Pawnee plant. The flying test bed, of course, had done a major portion of the development on the dynamic system and a lot of the certification, so things went pretty fast with the second prototype. It was put into service to get performance and stability and control, which couldn't be done on the previous machine. The initial flight of the second prototype was uneventful. This was about 2 years after we started the program and about 1 year after we flew the flying test bed. You notice that there's no stabilizer back here on the tail. Now this will change as we get into our development program because we had some stability problems requiring the stabilizer. Even though it was had been a lot of development prior to this, we took our time moving forward with the second prototype in case there were any problems that we hadn't uncovered with the flying test bed. This is a FAA required test, the application of 500 control cycles at full power. This was done on a turntable on the directional system. Numerous flights were made to altitude on performance and stability and control testing, and also to measure stresses in the dynamic systems under all flight conditions. The CH-1 helicopter had adequate forward speed to allow it to fly in formation with an airplane. With slight repairs, the fuselage from the static test was used to assemble the second prototype. On this machine, you'll notice that we installed a stabilizer on the rear that feathers into the downwash in hovering flight. We'll now observe a series of power-off landings, auto-rotation landings, that were conducted in order to get data for the handbook and required by FAA. And to do this, we fly in at a certain speed and height above the ground and cut the power off and make a landing. And then these data are presented in a graphical form and the techniques defined for pilots to use in the field. He's coming in here, nice chop power, flares the aircraft, levels out the flare, pulls in collective pitch. This would be another point, another speed or height. Cut the power. That was a pretty slow one. The CH-1C was initially certificated as a two-place helicopter. This limitation resulted from a lack of CG travel, and we could have stopped the program with FAA and corrected the stability problem, but we decided to proceed and get our initial type certificate and then come back and correct some of the things we wanted better performance on. The FAA approved performance was generally very impressive. The maximum speed, 122 miles an hour, which was some 20 miles an hour faster than most contemporary helicopters. It had a rate of climb of 1,000 feet a minute that it held almost all the way to 10,000 feet. It could climb to 10,000 feet at 2,600 pound gross weight in 8 minutes and 46 seconds, or 3,000 pounds gross weight, 11 minutes and 19 seconds. It had a limitation on altitude of 11,000 feet at 3,000 pound gross, which resulted from blade stall and forward flight. This was a deficiency we corrected later. Hovering ceiling at maximum gross weight of 8,600 foot on a 95-degree day, and out of ground effect at 6,000 foot with full gross weight, range of 290 miles, and endurance of 3.8 hours. It was really a step forward in the performance for small helicopters. The CH-1 was certificated as a two-place helicopter. This limitation arose because of high pitching moments on the fuselage, which in turn was a result of the streamlined fuselage shape and the high speed of the helicopter. On the CH-1, the horizontal stabilizer free-floated and streamlined itself into the rotor downwash and hovering. In forward flight, it moved into a horizontal position against a stop. On the CH-1A, this stop was redesigned to move and was linked to the fore and aft cyclic control. Thereby, the stabilizer acted like an elevator on an airplane, increasing the longitudinal control. With this change, it was possible to open the CG range and certificate the aircraft as a four-place. Demonstrations were made to the military both before the CH-1A was certificated and afterwards. A tour was made to the East Coast, to Washington, D.C., and demonstrated to numerous military people. They all agreed that what we needed to do was stage an evaluation in the mountains at Fort Carson and Camp Hale. So this was scheduled with the Army to be conducted in the fall of that year. And Sid Shannon arrived at Fort Carson and briefed Captain Knowles with regard to the helicopter. Jack Zimmerman's in the white shirt. Personnel at Fort Carson were also briefed on the helicopter, and then Captain Knowles and Zimmerman took off for Camp Hale. That's the mountains to the west Colorado Springs. The flight from Fort Carson to Camp Hale was made on a straight line, direct. And according to the Army, this is the first time that a helicopter had flown this route. En route, it was necessary to go as high as 17,000 feet in order to get safe clearance over the mountains. Jack Zimmerman and Captain Knowles arrived at Camp Hale. They have a runway there, but there weren't any other aircraft around. Helicopters have to kind of sneak up the valley when the weather's right to get in there, and they don't perform very well at this 10,000 foot elevation. Camp Hale is close to Leadville. We were there several days, made numerous flights around the area. And it's This is our hangar. They really didn't have hangar facilities. We could get most of the helicopter inside. We demonstrated hovering with 4 people aboard. And this really impressed the Army that we could have this kind of performance at this high altitude site. Below Camp Hale is at 10,000 feet. There's a number of 14,000 plus mountains. It's the one you see here in the background. And we landed on all of these mountains. There's another high peak there. And another one. The trip back to Fort Carson over the mountains was uneventful. When we arrived in Colorado Springs, we inquired with regard to previous landings on Pikes Peak and found there hadn't been any. So we called the plant in Wichita and suggested that while we were in Colorado Springs that we make the first landing on the peak. They approved it, and it took about 3 days to get it all set up. But at 7 o'clock in the morning on the 13th of September 1955, the Cessna helicopter made the first landing on Pikes Peak. We'll now go and look at some of the movies on this. Jack Zimmerman made his approach to the mountaintop from about 15,000 feet. And this was 7 o'clock in the morning, which we had to pick that time to avoid the traffic that arrives later. The Broadmoor Hotel had the concession, and but they agreed to this. Jack wore oxygen. He said he didn't need it, but we kept it on the safe side. And we landed up here. Then he picked up Captain Knowles, who'd been flying with us all week, and he ran a little hovering evaluation on the helicopter. Here he is aboard. And they had surplus power, so decided to load in another man. We didn't have a seat in the back, but we loaded him in behind the pilot, just on the floor, and hovered with 3 people aboard. Here we are with 3 people. We decided that was about the limit at 14,000 feet, so we didn't try to do anything with 4 people. I'd been concerned that waiting 3 days to get the press and the Army organized, that Bell Helicopter might hear about our endeavor and sneak up there with a Model 47 they had with a bigger engine in it for altitude work. But they did hear about it, but they didn't get there in time. Here's General Van Otten climbing aboard, and Jack flew him back down to Fort Carson to his command post. All went very well. Notice here he's climbing out from the peak. He's not just sliding over the edge. The Denver Post in the evening edition carried a complete story. See the helicopter here, and this is the parking lot. This photograph was taken from an airplane overhead. The Denver Post also reported on a second helicopter landing that same day. According to the Post, there was a frantic phone call made from the management of Bell Helicopter to Hersey Young in Denver, who had one of the Bell altitude machines, and they requested that he immediately go down there and land on the peak. So he came in later, and I didn't know him at that time, but later he came to Cessna wanting to buy the Cessna machine after he'd seen the performance reports on it. And it's too bad that he didn't arrive just after we did, because we could have challenged him to a weightlifting contest up there with the witnesses we had on hand. Sid Shannon, our sales manager, and Jack Leonard, general manager, were quick to follow up on a success of our tour to the mountains. And in the spring of 1956, we had a contract with the United States Army to supply 10 CH-1A helicopters. With the contract in hand, we continued to demonstrate the prototype to the military with it dressed in Army colors. The ink was hardly dry on the contract with the Army when the Continental Motors came to us and said they couldn't make these belts that drove the fans and the supercharger get consistent life. We had experienced a situation where one belt might go 200 hours and the next one would go 20. So they were throwing their hands in the air and offering us another engine. Instead of the old 470 engine, they were offering us the FSO 526 engine, which was used in the 620 airplane. This would give us 10 more horsepower, but it meant designing and building a new cowling, running through the complete drive system qualification, and our management said, look, this is not the Army's problem. We have 18 months about to deliver the first helicopter, and we're going to do it on schedule and on cost. So that turned on a real busy engineering program. The Continental FSO 526 engine, shown here installed in the helicopter, had a supercharger located on the front of the engine as installed, driven from the crankshaft with gears. The fan up here was a different type of fan than used on the previous engine. And these are oil coolers on the side for the engine. There's a similar oil cooler on the opposite side for the transmission oil cooling. This engine was used in the Cessna 4-engine pressurized high-altitude executive prototype that was under development at the same time. Looking at the back of the engine, this is a crankshaft output that drives the helicopter. Inside this housing are gears that transfer the drive up to this point, a horizontal shaft, and then another right angle gearbox that drives the fan. Looking down on the engine, we see here the fan, which is a large diameter fan. This is the inlet, and there's a dome in the center. It turned much slower than the other fans. This is the inlet air filter to the carburetor, and we see the oil coolers here again. Since it was necessary to rerun the qualification program, we decided to also improve the transmission. You will recall that we mentioned a blade stall problem at high altitude, so we speeded up the rotor. The ring gear pinion ratio was changed. The pinion, new pinion, had 6 teeth, the same as the original, but the ring gear was reduced from 51 to 49 teeth. This gave us a set of gears completely interchangeable with the other gears and an increase in rotor RPM. This was accomplished by the Fairfield Manufacturing Company that made our gears. The CH-1B was certificated in July of 1957. The first delivery of a YH-41 shown on acceptance flight here, was made in September. Lieutenant A.E. Lush was the test pilot that made the acceptance. Lieutenant Lush shakes hands with Bob Lair, our General Manager and Vice President of the Military Division of Cessna, as the local Army representative, and I look on. The first YH-41 delivery was airlifted to Edwards Air Force Base in a C-130. Before continuing with the evaluation of the YH-41 by the military, we will return to the Boundary Layer Control Program, which is contracted with the Office of Naval Research and the Army. This research contract was written in very broad terms, but early in the program we narrowed the objective to that of delaying the stall of the retreating blade on a helicopter rotor with the boundary layer control, and this would potentially increase the speed of the helicopter. The program progressed through analytical study stage into wind tunnel testing and then into flight test. The positive results of this program are shown in the final report, which was published in 1956. As far as I know, this is the only helicopter that ever flew with boundary layer control on the rotor blades. San Hinton and I discussing the boundary layer control program. San managed all aspects of this program. This sketch represents airflow from left to right over a flat plate. Those molecules of air in the close vicinity of the plate experience skin friction drag, and their velocity is retarded. As they flow to the rear, the boundary layer becomes thicker but extends to infinity, with the free stream flow pushing it along. This sketch represents airflow from left to right over a circular cylinder. We see that at the leading edge of the cylinder the pressure is high. This is the front stagnation point. As we move along the cylinder, the pressure decreases to a minimum at this point and then increases again to the rear stagnation point. Since each molecule of air on the front side is experiencing high pressure behind and low pressure ahead, the velocity increases. This applies to the free stream flow and also to the boundary layer. As we pass the minimum pressure point and go down the backside, the opposite occurs and the free stream flow decreases. However, in the boundary layer, which has experienced friction and loss to energy, the boundary layer velocity reverses at this point and the air begins to accumulate. In a continuous flow, air cannot accumulate. Consequently, the boundary layer that has reversed at this point and started to accumulate breaks away, and this reestablishes the flow around the complete cylinder. The pressure behind the cylinder drops to that corresponding to the pressure in the free stream behind the cylinder. This low pressure behind and the high pressure in front creates pressure drag, which is much higher than the skin friction drag we have discussed earlier. We now say the cylinder is in a stalled flow condition. This represents the flow over an airfoil that is operating in the unstalled condition. There's a high negative pressure well forward on the airfoil, and then the pressure becomes more positive toward the trailing edge. In this case, the boundary layer is making the pressure gradient, but is thickening. In this one, we have a slightly higher angle of attack, and the boundary layer is unable to make it against the pressure gradient and has separated at this point. Now, one way to delay or alleviate this separation is to remove the boundary layer forward of the separation point by sucking it through a slot in the airfoil. Then the high velocity air from above comes down and creates a stronger boundary layer that carries the flow to the trailing edge. A cast aluminum wind tunnel model of the rotor blade is provided with an insert which can carry different types of slot arrangements. One insert shown here with the slot. Now the boundary layer flowing along here is sucked down through that slot by an evacuation pump. This allows the high velocity air to move down behind the slot and create a stronger boundary layer that makes it on back to the trailing edge. Previous boundary layer control research had been conducted on heavily flapped airfoils or highly cambered airfoils, neither of which are suitable for helicopter operation. In addition, the tests had been run under steady state conditions, and the helicopter rotor blade goes through its angle of attack range about 5 times per second. The wind tunnel blade model incorporating the BLC slots was pivoted on the quarter cord and could be oscillated by an adjustable speed motor to provide angle of attack variations similar to the main rotor blade. The suction pump was separated from the model with a butterfly valve that was also phased to the drive mechanism, and it allowed the application of suction only at high angles of attack when it was needed. A series of pressure transducers were installed in the model that measured the instantaneous pressure along the cord, and these values were automatically integrated to read out either lift or pitching moment. A strobolux was also phased to the mechanism for the purpose of viewing tufts on the model during the oscillation. A multitude of inserts incorporating various slot arrangements could be installed in the wind tunnel model. This model was tested in the Wichita University 4-foot open return tunnel with a large number of configurations. The final configuration was confirmed in the 10-foot tunnel before the design of the helicopter rotor blade. The standard Cessna rotor blade made by the Pruitt Aircraft Company incorporated a roll D-section steel spar made of 4140 heat-treated steel. The skin was a stainless steel wraparound 9 thousandths thick, and on the inside was a sheet of hat sections which was bonded to the skin and the spar. This was a very rugged rotor blade, worked very well, but it was unsatisfactory for the incorporation of the BLC slots. The special rotor blade for the BLC program incorporated double aluminum skins with honeycomb in between. In the region of the slot there was a solid aluminum piece inserted to provide structural strength. The D-spar and the contour were identical to the standard blade. This section was fatigue tested prior to flight to substantiate it structurally. The BLC system was thoroughly tested on the ground test vehicle. Here is the engine located on the left, driving through a 3,000 RPM shaft to the transmission, then up to the simulated rotor. The suction pump is driven by a belt from the shaft, is actuated with a hydraulic clutch on the front. Air is drawn through this rigid ducting, a cyclic port valve, flexible ducting from the simulated rotor blade. The suction pump was designed at Cessna. It was a rotary vane type, incorporating 6 sliding vanes, was aluminum construction. At the inlet, it pumped a little over 1,000 cubic feet per minute at a pressure ratio of 2.7. It was 12 inches in diameter, 27.5 inches long. It turned 1,500 RPM and weighed 114 pounds. The lower half of the rotary port valve had an open slot extending approximately 90 degrees of azimuth. The rotating upper half had 2 ports that connected to the 2 individual rotor blades. Here we see the system installed in the helicopter. The pump is installed in the left forward seat position, the ducting on up to the rotor and then the rotor system. Movie camera was mounted on top of the rotor on its side. This orientation was necessary to get normal camera operation in the rotating environment of the rotor. Movie presents the rotor blade with the leading edge at the top. You'll notice the mid-span boundary layer fence, which restricts the boundary layer inboard from disturbing that outboard. The tufts located on the blade indicate the boundary layer control direction of flow. You notice outboard they just shift toward the tip as they go through the stall region, whereas inboard they actually reverse direction. In conclusion, first, the standard helicopter was rotor blade stall limited at 10,000 feet. With the BLC system installed, it flew 13 mile-an-hour faster, at which point it encountered control and power limitations. If the control and power limitations had not existed, it appears from the stall distribution on the rotor that it would have flown about 50 mile-an-hour faster. This polar plot is a top view of the rotor with the advancing blade at this point and the retreating blade here. This is forward. The black area represents a fully stalled condition of the blade, which is 50% of the airfoil being stalled. The gray area represents a 35% stalled area. This particular plot corresponds to the standard helicopter without BLC operating at its blade stall limit of 106 mile an hour at 10,000 feet. With the BLC system operating and with the helicopter flying 13 miles an hour faster at 119 mile an hour at 10,000 feet, the fully stalled region on the rotor was completely eliminated. This plot corresponds to a plot on the standard helicopter without BLC at approximately 50 mile an hour slower. The research program was concluded as a very successful program. Of course, there was never an effort made to address the problems of putting the system into production. The final BLC report was published in 1956 as a classified document. It was later declassified. The report contained all the technical information of the BLC program. We will now return to the military evaluation of the YH-41. In order to expedite the engineering flight test program, the first YH-41 was airlifted to the Flight Test Center at Edwards Air Force Base. Walter Hodson, test pilot, was assigned as the project pilot. Emmett Coley was the project engineer. Today we are very fortunate to have Emmett here with us and to give us a first-hand briefing of the Air Force YH-41 engineering evaluation.
The Air Force performed a performance and handling qualities flight test on the YH-41 at Edwards Air Force Base, California from January 1958 until February 1960. During this time period, we also performed a flight test on the aircraft at the high altitude site at Bishop, California. The Air Force findings were that the YH-41 did have as good a performance as was expected. However, it also had some rather serious handling qualities problems. We noted some mechanical problems with the aircraft, but this was not unusual considering the stage of development that the aircraft was in. Mr. Siebel at Cessna aggressively pursued a modification program to correct all of the adverse Air Force findings and was very successful in doing this. However, the time for the H-41 had already passed. Turbine helicopters were already on the horizon and it was too late. However, the H-41 did contribute significantly to the helicopter state-of-the-art in showing how to improve hot day, high altitude performance and improve helicopter handling qualities, as well as the technology for testing modern helicopters.
The following Air Force photographs were furnished by Emmett Coley. Here we see a photograph taken in 1958 with Lieutenant Coley and Captain Walter Hodson discussing the YH-41 program. The Air Force Flight Test Center received the first YH-41, serial number 64237. These documentary photographs were taken in October 1957. The YH-41 Edwards flight test crew, the crew chief, who I cannot identify, this is Captain Hodson, this is Lieutenant Coley, and Bill Osborne, who was the Cessna service representative at the base. The YH-41 panel featured Army radios of the day. The instruments were more or less standard except for a unique airspeed indicator. The airspeed indicator featured an inner movable dial graduated in terms of altitude. The adjacent surface of the fixed face had graduations in terms of aircraft weight. The pilot could align the operating conditions of weight and altitude using the knob on the left. In doing so, he positioned the red line on the instrument to the proper position. With this innovation, the FAA allowed a variation in the VNE, red line speed, with aircraft weight for the first time on a helicopter. This photograph shows the rotor hub. The inner hub was clamped with a series of bolts to the mast. There was no spline employed. The inner hub then carried a shaft, cross shaft, on which were needle bearings, one on each side. The individual blades had a individual outer hub part. At the center, there were two concentric bearings, a needle bearing which accommodated the flapping motion of the rotor, and then two plain bronze bearings concentric with the needle bearing that accommodated the coning between the two blades. The control motion came up through the center, operated on a pitch horn, and then through a torque tube, universal joint, another torque tube, and another universal joint. This mechanism here was a tracking mechanism, and by adjusting those bolts, you could change the torsional relationship of the two halves here and adjust the tracking. This is a force balance mechanism. The centrifugal force operating on this weight places this link in compression, and it is supported here so that the link is quite short. This has a destabilizing influence. In other words, as the pitch goes up, this will tend to push the pitch higher and vice versa. There were very few bearings, only the needle bearings in the center, and so it was free of the normal bearing friction oxidation problem. One of the early flex beam rotors, the blade attaching angles here consisted of 4 nested sheets of stainless steel sheet bent in an angle form. They were 35 thousandths thick and clamped together only at the end, so they twisted for both cyclic and collective pitch. The aluminum tail rotor hub had 2 needle bearings for flapping of the tail rotor. The hub also had steel tubes that ran out from the center to carry needle bearings that were pressed into the casting in the blade. The pitch change came up through the center of the shaft. There was a cross beam, pitch links, and the pitch horns, which were integral with the blade casting. The skins were chem milled to provide raised areas in the riveted portion. There was no bonding used on the tail. The Air Force Flight Test Center installed sensitive calibrated instruments for their flight test program. They filled all the open spaces in the standard panel and added additional instruments above the panel. A test air sensor was located forward of the left skid. This is the cowling. This unit was located forward from the fuselage and below the rotor as far as possible in order to get true flight, direction, and speed conditions. In-ground effect hovering performance was determined in tethered flight. In the center of the tether cable was located a load cell which measured the tension in the cable electrically. With this procedure, the helicopter was held in an exact position above the ground and the total rotor lift was determined. This procedure was used at 4 different elevations. Hovering tests were conducted at Edwards Air Force Base, 2,500 foot, at Bishop, California Airport, 4,000 foot, at Long Valley, 7,500 foot, and at Coyote Flats, 9,500 foot. The helicopter flight path was determined with specialized photographic equipment on the landing and takeoff tests. The living facilities at some of these high altitude test sites were definitely of the Boy Scout variety. We'll now proceed with the Army testing and evaluation of the YH-41 at Fort Rucker. Each month after the first delivery, 2 YH-41s were ferried to Fort Rucker. This is Butch Kerr, who flew the H-34 in and brought in the pilots and mechanics to pick up the H-41s. They then flew in formation on the return trip to Fort Rucker. These shots were taken at Fort Rucker at the post in front of the headquarters there. And the YH-41 was on test with two different groups at Fort Rucker. The TATSA group that evaluated the maintenance and of the machine and put as much time on as they could, and then the aviation board that evaluated it from a user's standpoint, as what could be done with the aircraft. TATSA really painted up the cowling. This is John Gary, who was a graduate engineer on their staff. This is the Army post at Fort Rucker as it appeared in the late 1950s. There have been many additions today, including a Army museum which houses the only remaining Cessna helicopter, a YH-41A. Bill Bird on the left and Captain James Bowman on the right. Captain Bowman was a project pilot for the Army Aviation Board in their evaluation of the YH-41 at Fort Rucker. Captain Bowman set an altitude record with the YH-41, and we will address that in a few minutes. It's the highest altitude, still the highest altitude ever reached by a recip engine-powered helicopter. Bob Smith is on the right. In preparation for an altitude record attempt, we made a number of test flights to high altitude at reduced weight to get engineering data. Here you see the oxygen bottle on the back of the aircraft to balance the removal of the cowl and battery and generator. On December the 28th, 1957, Captain James Bowman, flying the Cessna helicopter, set 3 records in 3 different weight categories, an unlimited weight and then 2 specific weights. The maximum altitude attained was officially 29,777 feet. The Army had previously held the altitude record at 21,220 feet, held by Captain Gaddis of the U.S. Army, also a member of the Army Aviation Board. Later, a French helicopter set a new record at 26,931 feet. That was June 1955. For setting the 3 new records and returning the world record to the United States, Captain Bowman received the Distinguished Flying Cross, which was presented to him by General Maxwell Taylor. This is the takeoff for Captain Bowman's altitude record. The weight had been stripped from the aircraft as much as possible. The cowling had been removed. The engine was started, and then the starter was removed. All the radios were removed. The cabin interior had been taken out. The doors had been removed and replaced with a plastic covering with a zipper in it. The landing gear had been removed. There were 4 hard points to set the aircraft on. Generator was removed and the battery. The aircraft ended up nose heavy, and accordingly the oxygen bottle was located as far aft as possible, but it still required some ballast on the tail skid. The takeoff weight of the aircraft was substantially less than the normal empty weight of the helicopter. A new calibrated altimeter was installed in the aircraft, which indicated an altitude of 30,335 feet. But the official barograph showed an altitude of 29,777 feet. By early 1958, all 10 YH-41s had been delivered. All pilots that flew the aircraft immediately recognized its outstanding performance. The official document, however, was published 2 years later in 1960 by the Air Force Flight Test Center at Edwards Air Force Base, California. The report presents the details of the flight test program. However, we will just review the conclusions. The performance of the YH-41 is good, and the aircraft has exceptionally good high-altitude performance. The contractor's estimated performance was met or exceeded with the exception of the hovering ceiling in and out of ground effect. Takeoff performance is very good. Only 250 feet is required to clear a 50-foot obstacle when operating at 9,000 foot altitude and a climb-out airspeed of 20 knots. Maximum rate of climb is 1,090 feet a minute at an altitude of 9,800 feet and 3,000 RPM. The maximum airspeed of 103 knots and the recommended cruise speeds of 87 knots are quite high for an aircraft of this size. Maximum range is 189 miles with a 10% fuel reserve. A short distance of 80 feet is required to make a maximum performance landing over a 50-foot obstacle at a density altitude of 10,100 feet. Here the report is pointing out that the payload capability is insufficient. That's on the basis of 3,000 pound gross weight and 200 pounds per person. It cannot put in full fuel. They also point out that the aircraft has sufficient performance, that if the approved gross weight was increased 3,200 pounds, it would be possible to do this. The maximum airspeed red line here was too conservative, according to the Air Force. Now, they base their findings on performance, whereas the FAA looks at it from a safety standpoint and force the manufacturer as an FAA-approved item to be more conservative. And here again, they're pointing out that the range lost by operating 3,000 pounds doesn't justify operating at 2,900, again the same philosophy. And then the rate of auto rotation was found to be quite satisfactory, and they could make landings at high altitude over 50-foot obstacles in a short distance. The YH-41 Stability and Control Evaluation Report was also published in 1960. However, the comments that went into this report were available from the military as early as 1958. The very favorable performance comments were not paralleled in the stability and control evaluation. The YH-41 in the configuration tested is unacceptable for service use. Its good altitude performance, as reported in the YH-41 preliminary report, gives it considerable potential if the numerous flying quality deficiencies are corrected. The lack of stability in this aircraft makes the rough air handling qualities unsatisfactory and would preclude safe instrument flight. Other than performance, the YH-41 exhibited the following desirable features: good lateral and directional maneuverability, good longitudinal and lateral control sensitivity, excellent directional control sensitivity, good static directional stability, sufficient control travel in rearward and sideward flight for speeds up to 30 knots, and visibility in all directions except diagonally over the YH-41 has unacceptable deficiencies in the following areas, which must be corrected before the helicopter can be considered satisfactory for service use. We will address these one at a time as we talk about the improvements we made and how we approached it. In our enthusiasm to produce a high-performance helicopter, we had neglected the handling qualities area and were behind the industry state-of-the-art. Early in 1958, we turned on a research and development program, not just to catch up, but to leapfrog the industry. And 5 months later, mid-year 1958, we were prepared to show the prototype to the customer. The only outward apparent change was a much wider aspect ratio stabilizer. This paragraph appeared in the introduction of the Stability and Control Report on the YH-41. During the course of the Air Force Flight Test Center testing, the contractor expended considerable development effort to correct the deficiencies noted in the preliminary data provided by the Air Force Flight Test Center and the Army test groups. Fixes for these deficiencies were incorporated in a YH-41 at the contractor's plant and were qualitatively evaluated by the Air Force Flight Test team on the 15th of July 1958. A report of this evaluation is given in the appendix of this report. Captain R.G. Ferry and Mr. V.K. Putnam visited the Cessna Aircraft Company of 15th to 17th of July 1958. The Cessna personnel demonstrated fixes in every major area that has been found on the YH-41 and described immediate fixes for nearly all of the numerous minor deficiencies, primarily maintenance items, that have been found from service tests. Air Force test personnel were highly impressed with this contractor's comprehensive and open-minded approach to the solution of these problems, and the outstanding progress which has been made in such a short period of time. The progress is commendable compared to past experience with other contractors in the rotor wing industry. In the paragraphs which follow, a brief evaluation is given of each of the fixes demonstrated. A continuous oscillation in yaw was apparent on the YH-41 in level flight. The lateral acceleration that accompanied the directional oscillation caused the pilot to be thrown from left to right. This was very aggravating in turbulent air. Cessna has practically eliminated this oscillation. The tail rotor redesign consisted of moving the skin on the blade rearward at the tip so that the center of pressure was behind the pitch change axis. This stabilized the blade, also increased the pedal forces by an imperceptible amount. The next item, the YH-41, was dynamically unstable longitudinally and in level flight exhibited a pronounced tendency to porpoise or pitch arbitrarily. These undesirable characteristics have been completely eliminated by a redesign of the horizontal stabilizer. Hands-off flight is now possible for extended periods of time, at least 1 minute. The long period oscillation still remains, however, it is a small amplitude, 5-10 knots, and is almost neutrally damped. This is not too objectionable, but should be improved. The horizontal stabilizer was much larger, had a wider span, more area, and a higher aspect ratio. It was free-floating, and in hovering it aligned itself with the rotor downwash. In forward flight it assumed a horizontal position and was controlled by the collective pitch. Although lateral stability was not a major problem area in the YH-41 in level flight, a mechanical driven gyro has been installed to improve the lateral stability. This gyro is connected directly to the lateral servo system and is all mechanical. This device provides deadbeat lateral stability. It is particularly impressive during cruise flight in turbulence and in hovering flight. During hovering, the YH-41 stability was very poor. Arbitrary oscillations in pitch and roll hindered precise control of the helicopter. Installation of this gyro has essentially eliminated all arbitrary lateral motions in hover and resulted in a marked improvement in the pilot's opinion of the handling qualities. The 10-inch diameter, 3.5-pound gyro, turned at 10,000 RPM, was driven by a flex shaft not shown from the transmission. This gyro was pivoted on a vertical axis. It was restrained by a leaf spring, centering spring, and by a damper. When the helicopter rolled, the gyro would precess on a vertical axis and feed control motion into the lateral cyclic through a mixing linkage and the power boost. The gyro was located in front of the left cyclic stick. Here we see the gyro wheel, flex shaft that drove it, and the linkage to the leaf spring, linkage to the damper. You notice that the gyro moves the lateral controls without moving the cyclic stick. And it is very heavily damped. This gives the helicopter position memory. Another item, the sudden and lateral trim change that was required following a power failure in the YH-41 was very objectionable. A device has been installed by Cessna which automatically makes this lateral trim change without moving the cyclic stick. This is actuated by changes in manifold pressure. With this installation, no lateral control movement was required by the pilot following a sudden power failure. This schematic shows the carburetor, the supercharger wheel, and the power trim cylinder. By flight test measurement, we determined that the pressure rise across the supercharger wheel was at all times proportional to the lateral trim change. By introducing a simple cylinder with an internal spring, an output was obtained which was proportional to the trim change. This worked through a mixing linkage into the lateral cyclic to nullify the trim change. Captain Ferry and Keith Putnam summarized their observations as follows. With the improvements that were demonstrated in the YH-41, Cessna model CH-1C, in its present state of development, would be satisfactory for instrument flight. With only slight further improvements of the longitudinal and directional stability, the YH-41 CH-1C would be the most stable helicopter mechanically stabilized in operation today. The final report on the stability and control was published 2 years later in March 1960. We've reviewed the appendix which reflected the improvements to the handling qualities, but the basic body of the report still reflected the poor handling qualities of the YH-41. One YH-41 was modified with the improvements and returned to Edwards Air Force Base for further evaluation. With the stability improvements in hand, Cessna decided to offer the helicopter as a commercial product. The type certificate on the CH-1C was issued July the 28th, 1959. This is Jerry Poland, the sales pilot, taking a pilot. The primary purpose of the helicopter was personnel transport, although kits were approved for a number of other functions, as we'll look at here right away. External cargo could be carried on cables with a mechanical hook which had an electric release that could be actuated by the pilot in the case of an emergency. This kit was approved by FAA for the hauling of external cargo at reduced airspeeds. Here, a telephone pole is being carried externally. A personnel hoisting kit was developed which allowed hoisting of personnel in areas where the landing area was unsuitable. Here is the motor that drives the drum. It's mounted on the right side above the pilot, and the cable runs across and down. The sling can be taken inside for transit. In flight, the sling is lowered down, door is held open with a latch. This is the sling that the occupant puts under his arms. Melvin Begg, project engineer, is demonstrating it. Pulled up between the skid and the fuselage, and then enters into the back seat. The operator, hoist operator, has a side-facing seat. The door is then closed by unlatching and flying forward. A float kit was developed for use over the water and in marshy lands. It was a rubberized, lowly pressured bag, typical of other helicopter floats. A number of auto rotations were made onto Lake Afton, west of Wichita, to establish the auto rotation landing characteristics on water and also the maximum water contact speed that could be permitted. Its handling qualities on water and on floats was typical of small helicopters. The cowling is retained with quick disconnect fasteners. Here Jerry Poland demonstrates the easy removal of the cowling. With the cowling removed, the carburetor, starter, magnetos, and supercharger are all readily accessible. For balance reasons, the battery compartment was located in the tail boom. This access door provided access to the battery and the tail rotor drive shaft damper. Here Jerry Poland demonstrates the CH-1C hands-off stability. To further demonstrate the inherent stability of the Cessna CH-1, Jerry Poland, while flying alone in the aircraft, climbed out of the front seat into the right rear seat. When this photograph was taken, he was holding up 4 fingers to signify that he had been in the back seat for 4 minutes. Jerry demonstrates an auto-rotation landing. Here we see he's lowered the collective pitch, reduced the throttle, and on the tachometer the engine and the rotor are synchronized. As he cuts back the throttle, the engine RPM drops down. Now the rotor is in auto-rotation. The RPM increases as he lowers the pitch. He's approaching, gliding toward the touchdown point, which will be over here. He'll raise the nose as he flares the aircraft, approaches the landing site, pulls the nose up in the flare. Now from the outside we see the helicopter gliding in. He pulls the nose up in a flare. As it settles toward the ground, pulls in collective, cushions the landing. Cessna entered the commercial helicopter business in earnest in 1961. The Cessna helicopter was given the name Skyhook to fit the family of fixed-wing single-engine airplanes Skyhawk, Skylark, and Skylane. The Cessna brochure shows the businessman pilot with his luggage in the rear. The airplane single-engine marketing and service departments handled the helicopter as if it was another single-engine airplane. The Cessna brochure shows 4 businessmen on a business trip. By this point in time, the helicopter activity had lost its division status. The helicopter department was responsible for engineering and experimental activities. The helicopter manufacturing was in the Military Division Manufacturing Department, and the commercial sales in the Commercial Division Single Engine Airplane Department, and was handled through the normal airplane distribution system of dealers and distributors. During the summer of 1962, more than 10,500 persons had a spectacular view of the Century 21 World's Fair Exposition in Seattle through the window of the Cessna Skyhook. The Skyhook, chosen by the World Fair Council as the official Century 21 helicopter, was the only rotary wing aircraft allowed to operate out of the fairgrounds. From a heliport built atop one of the buildings in the center of the exposition, 3 Skyhooks conducted regular air taxi service to and from the surrounding area. The schedule included Seattle-Tacoma International Airport, nearby motels, the Seattle waterfront, and Bellevue. Here we see the Cessna helicopter flying past the $4.5 million Space Needle. The aircraft were owned and operated by Seattle Helicopter Airways. This is one of Seattle Helicopter Services schedule sheets. On the left here we see a map of the landing points, and which they ran on a regular schedule, and on the right are pictures of the helicopter. They equipped their helicopters with an additional seat and could carry 4 paying passengers. In the summer of 1962, Cessna made the first commercial application of the hoist system. This is a church steeple, and the cross on top of this steeple was rotating in the wind. It was about a year old, and they were afraid it was going to fall off of there. So the Volmer Construction Company hired Cessna to lower a steel worker down, which we did on the personnel hoist. And then he riveted with an explosive rivet gun the steel cross in position, secured it. Jack Zimmerman was flying the helicopter. Melvin Begg, project engineer on the CH-1C, was running the hoist. The line here between the helicopter and the worker remained slack but attached during about 10 minutes of work that he had to do. He had to reload his gun between each shot. It was a single shot, so it took a little longer. And of course Jack had a difficult job because he had to hover almost motionless close to 200 feet above the ground where there wasn't any good reference. Of course Melvin Begg was directing him with the intercom. Now the steel workers climbing back in the helicopter and getting ready to depart. Job's done. It will be recalled that the flight test personnel from Edwards Air Force Base and from the Army Aviation Board at Fort Rucker had evaluated the stability improvements by flying the Cessna prototype at the Cessna plant during the summer of 1958, and that they had found the improved helicopter now satisfactory for instrument flight. FAA approval of this configuration for visual flight only was obtained in the summer of 1959. Cessna management decided to pursue the Army instrument trainer requirement, which was being generated within the Army. 2 programs were initiated at Cessna to pursue this business. First, the type certification was sought with FAA for the instrument flight approval. And second, a tour was organized to demonstrate the CH-1C to the appropriate Army pilots. Most of the demonstrations were in Washington, D.C. and at Fort Rucker. Jerry Poland conducted the tour and was assisted by a well-qualified demonstration pilot, Hersey Young. Hersey Young was a helicopter operator from Denver and was on contract with Cessna for the demonstration tour. He was a retired airline pilot, and with his extensive helicopter flight experience, he was an excellent pilot for the task. Following the tour, a number of letters of testimonial were received, and this is typical from the Department of Rotary Wing Training, United States Army Aviation School at Fort Rucker. It was addressed to Jerry Poland at Cessna. I hold an Army Special Instrument Rating and a Standard Instrument Rating in helicopters. During the period of testing of the CH-1 at Fort Rucker during February 1959, I flew the aircraft for 1.5 hours. Approximately half of this time was flown under simulated instrument conditions. Under both visual and simulated instrument conditions, the YH-41 seemed unusually stable and was smoothly responsive to the controls. I would be willing to fly it without hesitation under normal actual instrument flight conditions. Signed, Raymond E. Johnson, Lieutenant Colonel, Director, Department of Rotary Wing Training. The Army was happy to loan us a YH-41 for the IFR certification flight test program. The aircraft was brought up to the CH-1C configuration, YH-41A with the big stabilizer. Strakes were added here for dihedral stability effect, and on the nose was mounted the glide slope antenna. The side view of the helicopter shows the dihedral strakes better. The instrument panel was indeed full. You'll notice the 5-inch diameter attitude and directional gyro instruments on the pilot's side of the cockpit. When the FAA certificated the first helicopter, the Bell Model 47, it disallowed the use under instrument flight rules because the helicopter did not possess stick-free stability, otherwise known as stick force stability. So the precedent was set at that time that if a helicopter was to be certificated under instrument flight rules, it must have control force stability, and that then became our task on the IFR certification. This picture here was taken in Denver when I was getting my helicopter rating. This is a schematic of the longitudinal control force system which was added to meet the FAA requirement. The system first had at the top of the stick a trim switch which operated an actuator. The stick was pivoted here. This schematically is the output of the 4.5 cyclic to the helicopter. And then on the bottom of the stick is the actuator which operates a trim spring, thereby changing the 4.5 trim position of the stick. Also on the bottom of the stick is a bellows which is pressurized by external ram pressure. This pickup's on the outside of the aircraft. Now this system will destabilize the longitudinal oscillations of the aircraft, and it was necessary to add a G valve which basically bled the pressure on the bellows in such a phase relationship that it would stabilize the longitudinal motion, and it was actuated by up and down accelerations of the aircraft. This is a plot of stick-free static longitudinal stability of the IFR helicopter. Here we see plotted the stick force, vertical axis, and the airspeed, calibrated airspeed on the horizontal axis. The aircraft is trimmed to here at 50 miles an hour, and it takes a pull force on the stick to fly slower, and it takes a push force to fly faster. This shows the helicopter's long period longitudinal dynamic stability, pitch attitude versus time, and it is a pull and release maneuver. Here we see the graph. Pitch attitude is plotted vertically, time in seconds, along the bottom. The stick is pulled back and released, the helicopter nose goes up, and then of course it comes down and up and damps out very rapidly. This shows the very high effectiveness of the G valve. The directional control force system was designed on the same philosophy. Pressure was picked up on the outside of the aircraft from two ports on a drum, a cylinder, and these ports were located at 90 degrees. This also could be rotated for directional trim. The pressure from these ports fed into the bellows system, and of course it was sensitive to yaw angle as well as dynamic pressure. The bellows then operated through mechanism into the directional control system. The G valve was located back on the end of the tail boom and was very effective in damping out yaw motion. The FAA issued the first helicopter IFR type certificate to Cessna July the 7th, 1960. Harold Hermes and I presented a technical paper on the program at the January 1961 meeting of the Institute of Aeronautical Sciences held in New York City. Harold Hermes was the chief flight test section in the Kansas City FAA regional office. He was the FAA project pilot on the IFR certification program. The IFR prototype was the only helicopter built in this configuration. Although the FAA certification added credibility to the superior handling qualities of the Cessna helicopter, the Army had found the CH-1C satisfactory for instrument flight without the force field systems required by FAA. The Army procurement of the CH-1C for instrument training appeared quite favorable. Cessna helicopters were approved by the FAA on Type Certificate 3H10. There were a total of 6 models approved. The original Type Certificate on the CH-1 was issued in June the 9th, 1955. The CH-1A, as you recall, was a change from a 2-place to a 4-place approval. The CH-1B was brought on by an engine change from the 0470 to the 526 engine. The CH-1C was the incorporation of the stability improvements and auto-rotation improvements. The CH-1C IFR was the force field system added to meet the IFR requirements. There was one more model not listed on this type certificate, the CH-1D, which was issued in December of 1962. The gross weight was increased to 3,200 pounds, and the aircraft incorporated an improved engine from Continental Motors, still a 526, but with mechanical improvements. The Continental engine used in the helicopter was originally developed for the Cessna Model 620 high-altitude executive transport airplane. The helicopter and the airplane versions of the engine were operated at comparable powers and RPMs. However, the helicopter engine operated continuously at high RPM, whereas the airplane engine RPM was high only for takeoff. The engine crankshaft and connecting rods were stressed above the fatigue limit at high RPM and reduced power by inertial loading. This situation led to a number of service connecting rod and crankshaft failures in the helicopter engines. Cessna discontinued the Model 620 airplane shown here in 1957. because of the disappearing market due to the flood of reciprocating engine airliners entering the market as the jets arrived. The only home left for the engine was the helicopter, and Continental was reluctant to spend more on the 526 engine. The engine fixes didn't arrive until 1962 on the CH-1D helicopter, a bit late to avoid a poor reputation. In 1960-61, the Army sponsored a competition on the light observation helicopter. This is Cessna's full-scale mock-up of the proposed aircraft, with the engine located in the rear low, 360-degree visibility, avionics in front. The doors slid back on rails. And of course, Cessna wasn't successful in the competition. Sanford Hinton and Harold Farthing, San projected the program. In 1962 and 63, Cessna delivered some 15 YH-41A helicopters into the military aid program. Here we see a helicopter being removed from a shipping box at the airport in Tehran, Iran in 1963. Iran had requested the YH-41A because of their high altitude performance requirement in northern Iran. Notice the saddle fuel tanks on the side of the helicopter for extended range. These photographs were provided by Robert Pemberton, who was in Iran at that time. Initial deliveries were made to South America and to Iran. Eventually, the South American helicopters were also transferred to Iran. Cessna continued to deliver helicopters into the MAP program in 1963 after they had announced that they were getting out of the helicopter business. Well, folks, that is the summary of Cessna's 11 years in the helicopter business. On December the 26th, 1962, Cessna announced that it was departing from the helicopter activity. A few days prior, the FAA had issued the type certificate with a revision that added the model CH-1D, which featured the 3,200-pound gross weight and an improved Continental engine. The helicopter was the only instrument-approved helicopter. It had outstanding performance and held the altitude record. It was a well-styled, good-looking helicopter. Over the years, Jack Zimmerman had done essentially all of the experimental flying. On a number of occasions, he was encountered with mechanical problems in flight, which one would expect might lead to an accident or an incident. However, in Jack's professional hands, these incidents and accidents did not occur. Likewise, Jerry Poland and Hershey Young had flown the aircraft around the country, making extensive demonstrations with a flawless safety record. However, there were other pilots, both at Cessna and in the field, that were not as fortunate. And there were a number of accidents, and unfortunately, some of these had fatalities. Cessna had built 50 helicopters, approximately. In the inventory that the Army retained, they remained in service. And in the military aid program overseas, they remained in service. However, Cessna repurchased all of the commercial helicopters and destroyed them. At the time, the Army had an instrument trainer requirement with an initial buy of 80 helicopters. This business appeared to be in the bag. In addition, the military aid program was expanding with those countries that had an altitude operational problem requesting the Cessna machine. So then why did Cessna decide to depart from the helicopter business? Well, I didn't have the opportunity to sit in the management meetings that led up to the helicopter decision, so we'll have to speculate a bit. At the time, the turbine engines had moved into the aviation picture much more rapidly than anticipated. Cessna had encountered a problem with their Model 620 4-engine airplane, and they had to drop it before it really got started because of the reciprocating engine airliners moving into the used market as the jets arrived. By 1962, it was apparent that the turbine engine was going to take over the helicopter field, and all new helicopters were being designed around this. Now, the CH-1 could be expected to continue with increasing sales for a period of time, both in the military aid program and in the instrument trainer Army program. However, eventually Cessna would have to invest in a new helicopter development to have a turbine-powered helicopter that would be competitive. I believe that management had held out great hopes for the light observation helicopter program conducted by the Army, which could have provided funds to assist on this development. However, this assistance went to the competitors of Cessna in the helicopter business. In addition, Cessna could see that they would need to invest heavily in their primary product line, the fixed-wing airplane, in order to get this product line modernized and using the turbine engine. Another item I'm sure that was of importance was the product liability situation, which was beginning to explode. And they were witnessing product liability problems both in the fixed wing and in the helicopter. So the decision was made to get out of the helicopter business. It's interesting to note that today Cessna continues to be a very successful company, and all of their product line is built around the gas turbine engine. The product line that existed in 1962 and its derivatives has long been gone, dropped from production. Since 1962, on several occasions, editors of magazines have picked up the Cessna helicopter story as a matter of historical interest. The July 1974 issue of Private Pilot magazine featured an article by Cass Thomas. It was entitled, "The Skyhook, a Helicopter 10 Years Ahead of Its Time." The editor of Aviation International News requested that I prepare an article for publication in his magazine concerning the helicopter at Cessna. This article was published May the 1st, 1990. Well, folks, that completes our presentation on the Cessna helicopter. Today is April the 10th, 1991. I'm Charlie Siebel.